Oh, okay. So thanks, Anton, for the invitation, and it's nice to be able to talk to everybody today. I am mostly going to be focusing on the very simple Poisson case of symplectic manifolds, so the case of one symplectic leaf. But I'll make mention of more general Poisson geometry in some cases. I'm telling you today about some joint work of mine with Liat Kessler and also with Liat and Sue Tolman that's ongoing, and hopefully that the preprint with Sue will be out soon. So the overview of the talk, and I'll sort of give you the punchline of the talk at the beginning and then tell you a bit more about it. So the overview is studying the relationship between the geometry or topology of a circle action on a four-manifold and understanding the relationship of that data to some set of combinatorial data that you would associate to a circle action on a symplectic four-manifold. There is, this question has a long history. It goes, that there were studies by four-manifold topologists looking at classifying torus actions on four-manifolds and classifying circle actions on manifolds up to homeomorphism or diffeomorphism or all of that sort of thing. And so I want to focus today on the case where I have a symplectic manifold, so a symplectic structure around, and I'm looking at a circle action that preserves that. And I want to study this same question, relating the geometry or topology of this space on one side and the combinatorial data that you associate. And so what I'm specifically going to talk about is how to extract from that information a particularly nice description of equivariant cohomology. And so I'll talk a little bit about what I mean by that. And I'll talk about the different ways you can describe cohomology. And this all is, so it's the question that Sue and Liat and I answer in the case of four manifolds has a more general story, but the generator and relations description only works for four manifolds. But the more general story has to do with toric actions and complexity one actions, which I'll define. And the question is, once you have, once you reduce once you reduce to this generators and relations description, what does that presentation determine? What can you tell about the original manifold, about the original action? And the answer, the sort of ruining giving you the punchline at the beginning, I guess actually this is what I've learned by being chair, is that deans like to hear the bottom line up front. They want to hear the answer before you tell them all about it, and then they don't usually read all about it. So the bottom line up front is that what we can get from this generators and relations description is the equivariant diffeotype. So the diffeomorphism type of the manifold together with the action. But we cannot see the symplectic structure, which is I'll explain why it's not too surprising that we can't see the symplectic structure. And we also actually can't recover the complex structure. So there's just in terms of how we explicitly construct things, complex structures get messed up. Okay, so the starting point is a symplectic manifold. So we have a smooth manifold together with a closed and non-degenerate two form. The linguistic note is that the word symplectic was coined by Weil in his 1939 treatise on Lie groups, on linear algebraic groups, and previous to Weil, the group preserving a linear symplectic structure was sometimes called a complex abelian group, I think was the word used, which is not very telling to a geometer today. And so Weil coined this term where he translated the word complex. I mean, there's of course a related notion of preserving a complex structure, and he translated that into Greek. So the Greek syllable by syllable translation, com means together, and that gets translated into sim, and plexus means braided, and the Greek, just the Greek word for braided is plektikos. So that's where the word comes from, just a linguistic curiosity. The consequences of being symplectic. So the fact that the form is closed, I guess this has consequences that I haven't laid out, but this has topological consequences, which we'll see a bit about. This has topological consequences because, of course, it means that this form can represent something non-zero. It is a possible form representing something in cohomology. And if M is compact, that has to be non-zero. But the non-degeneracy of the two form, that also has consequences. In particular, the manifold has to be even dimensional and orientable. And I think these facts are sort of familiar, I guess, to anybody in a Poisson geometry seminar, so I'm not going to belabor that. There are abundant examples, and this is one place where I can say for the first time where I can, well, the only place where I'm going to sort of mention a non-zero, a more general Poisson structure. So we have these nice families of examples, projective space, Grassmannians, flag varieties. These are all sort of symplectic leaves for the Lie Poisson structure. On the dual of the Lie algebra. So in this case, on U of n star, or more generally G star. So those are all nice examples where we might want to ask things about the topology of the manifold. More generally, smooth complex projective varieties, smooth toric varieties are examples that a symplectic geometer might think about. And these toric varieties in particular, so toric varieties, I will spend a lot of time, or I'll spend some time telling you a bit about the story. The toric varieties have this nice relationship between, so a toric variety, let's call that, well, I'm on the compact manifold side, so I'll call it M delta. I want this draw. M delta together with its torus action. So the geometry and topology of that manifold can be encoded precisely in some combinatorial data, and that data to a symplectic geometer will typically be a polytope. And to an algebraic geometer, they will more likely be thinking about a fan. But these combinatorial data are, well, actually, they're not quite equivalent. So the fan, which is the normal, the vectors of outward pointing, did I draw it that way? Inward pointing normal vectors. Oh no, I did do outward pointing. No, I didn't. In any case, the normal vectors to the facets of the polytope, I've drawn it actually upside down. So if I draw the polytope here, I can see the polytope upside down from the right hand side. But the fan contains the information of the sort of combinatorial type of the polytope, but it doesn't tell you anything about the size. So I could just make this a little bigger, and I still have a polytope that is the normal vectors of those rays, that has those rays as normal vectors. And so already there, that's where we can see that somehow this combinatorial information may not tell us everything symplectically. So the size of the polytope that I draw has to do with the symplectic volume of the manifold, and this fan does not capture that. Okay. Okay, questions there? And I can also, I have the
Tara, maybe
yeah.
Like just the one word. How do you construct a fan from the polytope again? So you right, the
yeah.
polytope does determine the fan.
Let me add a. Oh no, that's not what I want to do. So, so you're asking, how do you construct the polytope from the fan?
Oh, I thought the other way around, right?
Yes, the other way around. Thank you. Okay, sorry. Okay, and of course I'm belabored by the fact that I haven't defined fan or polytope, but okay, I'll see what I can do. So if we have a fan, if we have a polytope, the polytope is defined to be the points in some Euclidean space such that the pairing of x with the inward or outward pointing normal vectors is less than or equal to alpha I. Okay, so these are normal vectors to the facets. And then the fan that these would, so if I call my polytope delta, then I get a fan from sigma delta whose rays are precisely those normal vectors. Whoops, sorry. And the cones of the fan correspond to precisely those collections of normal vectors such that let's see, so the normal vector nu I is, say, the normal vector, let's do this. Let's say the normal vector nu I is normal to the facet fi. So, oh goodness. I think this is, yes, okay, so this is going to be, we will have a cone in the fan whenever the corresponding facets don't intersect. I think I have that right. And so in this way, you can construct a fan that is, so a fan is a collection of cones. So without going into too many details, that's roughly how you go from a polytope to a fan. And we can see precisely here what we're losing is these alpha i's, which tell you how far apart how far apart the facets are, how far away the facets are from the origin, say.
Okay, thanks.
Okay. Okay, so in this way, the fan has slightly less information than the polytope. Okay, so that's that. Okay. So what I want to talk about in the context of these toric manifolds, or sort of more generally in the symplectic context, I want to talk about manifolds that have some collection of group actions. So I'll be looking at Hamiltonian actions. Those are actions that preserve the symplectic structure. And in addition, there's an additional sort of differential equation, set of differential equations that you require to be satisfied. You sort of require the vector fields that the action generates to be Hamiltonian vector fields on your manifold. And this is equivalent to saying that you have a momentum map or a moment map or a momentum map. Oh, I'm talking to Geneva. I guess I should use momentum. So we have a momentum map that's a map from the manifold to the dual of the Lie algebra. And the idea here is the components of this momentum map are Hamiltonian functions for the vector fields that the action generates. And these are all Morse functions in the sense of Bott. on manifold M. So this moment map gives us sort of one of the two big tools that symplectic geometers use. So this moment map is called by some people a soft tool. It leads us to questions that you can answer with Morse theory. It leads us to Betty number kinds of calculations and that sort of thing. And the two types of tools that are typically used in symplectic geometry are these soft tools, and then on the other hand, hard tools that sort of require the use of holomorphic curves and that sort of pseudo-holomorphic curves and their generalizations. And so that's sort of a big picture description of the types of tools symplectic geometers use. Okay, so not to belabor that. The thing that I want to talk about, so where I eventually want to get to, is talking about the cohomology, how you might use this momentum map, how you might use Morse theory to say something about the manifold. So I want to talk a little bit about the consequences that you can derive. The first goes back to a theorem of Ted Frankel from the 60s. He proved that if you have a Hamiltonian action on a manifold that's not just symplectic, but one that also has a compatible complex structure, and the action is actually preserves that complex structure as well. So in this context, so if we have a circle action on a symplectic manifold, preserving the symplectic structure, preserving the complex structure, then this action satisfies the additional differential equation. It has a Hamiltonian function precisely when the action has fixed points. So this, what I mean to say here is that this being Hamiltonian somehow is related to, is intertwined with this question of fixed points of the action. And Dusa McDuff went on to prove that this is true, this equivalence between Hamiltonicity and existence of fixed points. This is true generally in the four-dimensional framework. So for a four-manifold, we still have the equivalence with fixed points, but then she constructed a six-manifold that has fixed points, but which is not a Hamiltonian action. And so this example, in light of Frankel's theorem, this is not a Kähler. Not a Kähler example, of course. And I guess there is later work. So she was not assuming that this was Kähler either, but we will see that in this context, these are all Kähler.
Tara?
Yeah.
Just a possibly stupid question. Are they assuming any compactness at all?
Thank you. Yes, this is compact. This is compact.
Okay, thanks.
Tara?
Yeah.
When you say these are Kähler, you mean when it's Hamiltonian or general?
When it's when it is Hamiltonian.
Okay. Thank you.
Yeah. Yeah, okay. And oh, right, what I should have said here, so these examples, in these six-dimensional examples, so where we have an action preserving a symplectic structure, but which is not Hamiltonian, the fixed sets are two-dimensional submanifolds. And this is sort of in contrast. Many of the examples that the sort of long list of examples that I cited before, all of the flag varieties and coadjoint orbits, those by contrast all have isolated fixed points. And so somehow a natural question is, well, can you even do better? Can you make the fixed points isolated? And so Tolman did provide examples where there were 6 manifolds with symplectic actions, but only isolated fixed points. And Sue Tolman and her student Zhang have done further work to optimize the number of fixed points to, I think they have it down to, first they got it down to say 16, a power of 2 fixed points, 16 or 32 fixed points. I can't remember which power of 2. And they did that by, it's a very hands-on construction. They take a K3 surface and desingularize it and provide a circle action that is very explicit. But then they have further examples where they can sort of get rid of the fixed points. And I think they have an example which only has 2 fixed points. Okay, so that question is sort of relatively well understood. Okay. Okay, so if we restrict ourselves to the Hamiltonian setting, so here I want to not just here I'm assuming that the action is Hamiltonian, and if we restrict our attention to not an arbitrary Lie group but specifically to an abelian Lie group, then we have the first instance of a convexity theorem. So if we have if we have a torus acting on a compact symplectic manifold, then Atiyah and independently Gilliman and Sternberg in the 1980s proved that the image of this momentum map must be a convex polytope. It's a convex set, and it's a polytope because it turns out to be the convex hull of the images of the fixed points. So this again is some indication that the fixed points are playing some special role. Let's see. So the question I want to take away from this is, what does this? What can you say anything about what this convex polytope tells you about the original manifold and the action on the manifold? And again, these are soft tools because we are we're looking at the momentum map rather than at any holomorphic curves. One key point, so if we have an N torus acting on a manifold, it is true. So the vector fields that the action generates, in the case of an abelian Lie group, the vector fields are span isotropic subspaces of tangent spaces of the manifold, and so that guarantees that there can be at most half the dimension of the manifold many such vector fields, commuting vector fields. And so that tells us that the torus has to be at most half the dimension of the manifold for such an action to exist. I'm assuming this action is effective. So no subgroup is acting, no positive dimensional subgroup is acting trivially. What in the case when you have equality, so in the case that precisely a half-dimensional torus is acting on a manifold, there is a theorem of Delzant precisely classifying these toric symplectic manifolds in terms of the combinatorial data phi of M. And so the theorem is that toric symplectic manifolds are in one-to-one correspondence with certain polytopes, and the polytope in the case of an example is that phi of M. This polytope has to satisfy certain properties, so it is simple. It has precisely n edges incident to each vertex. It is rational, so the edges point in lattice directions in the well, we're in I've made an identification with the Euclidean space, and I can identify the lattice as the, oh gosh, I'm identifying the Lie algebra and its dual, but the lattice then is the kernel of the map from the Lie algebra to the group. These edges point in lattice directions. It is smooth, so that means that the n edges at any particular vertex, the n edges are a lattice basis of the lattice. And okay, and then polytopes in Rn. Okay, so those are the three requirements of a polytope. And so once you have each of those requirements, so one direction of this one-to-one correspondence is easy. Take a manifold with a Hamiltonian action, produce the momentum polytope. The other direction, given such a polytope, so given such a polytope, going backwards and producing such a manifold, I'll just say that M delta is defined to be some Euclidean space, some complex d-dimensional vector space, and then it is you create this by symplectic reduction at some alpha. The alpha is determined by those alpha i's that I wrote down quite a while ago, defining the polytope as a intersection of half spaces. So I won't go into the details, but you construct such an example by symplectic reduction. And I guess I think that's all I want to say about that. Oh, I already had made a slide of that. Okay, so this is saying the same thing. If we take such a manifold, we produce its moment polytope, and going backwards, we produce a symplectic quotient. And of course, the one-to-one is when you say one-to-one, what do you mean up to? On the left-hand side, this is up to equivariant symplectomorphism. There are and this will come up in a bit, actually. There can be different Hamiltonian torus actions on the same manifold. So for example, S2 cross S2, depending on the symplectic form, can have many different Hamiltonian two torus actions on it. And on the right-hand side, the equivalence is up to SLNZ, so up to affine equivalence. So SLNZ, you can shift around your polytope, and then up to translations around Rn, and the translations just correspond to choosing different constants to define your moment map. Okay, so that's that. And from here, there has been quite a bit of work understanding the topology of these manifolds, writing down. So there are multiple ways to prove this, but you can determine both the equivariant and ordinary cohomology of the manifold in terms of generators and relations. So here, given a toric manifold coming from a polytope, the polytope, I'm going to say, has some description like this, for I equals 1 up to n. This capital N is the number of facets in the polytope, and that capital N shows up here. So I take as generators for equivariant cohomology, I take one generator for each facet. These each have degree 2. And then I mod out by the ideal generated by, well, this is called the face ring of the polytope. So I am killing a monomial whenever the corresponding facets don't intersect. And then you can add to this. So this is the ideal I, and to get the ordinary cohomology, you have to kill some additional linear terms in the xi. So this is known as the Danilov-Yurkovich theorem. And from this led to a significant amount of work in combinatorics. Valera and Lee and Stanley were key players in terms of identifying precisely which combinatorics can show up, proving that the Betti numbers have to satisfy certain properties, and proving that face rings have to that face rings of this sort have to satisfy certain properties. From there, Masuda has done some work showing that from this presentation, so R, I'm calling this ring R, this face ring R, the equivariant face ring, and if Masuda proved that if you know both R and you know the first Chern class, so you know which element of this ring in degree 2 is the first Chern class, from this you can reproduce the polytope delta, and then of course by Dalzon's construction you can reproduce the manifold. So to some degree, for toric manifolds, the equivariant cohomology, together with a little additional information, lets you reproduce your manifold up to equivariant diffeomorphism.
Sarah?
Yes.
Hi. Masuda is about polytopes or about fans?
You have read this paper more recently than me, perhaps. Maybe this is about fans, actually. Should I say that?
I think Masuda is interested in storage varieties.
Okay, we'll say fans. Okay, so not to belabor this point. So, but this is again, this is about so again, this is not seeing, I guess that's the point, doesn't see symplectic structure. Okay. Which again is not surprising. In the most simple case, we are looking at a two-dimensional manifold with a circle action, and the moment map doesn't have very many possibilities. It's an interval, and you can't really tell from this equivariant cohomology ring how big that interval should be, which is equivalent to knowing how big the symplectic manifold is, how big the symplectic form is. So we don't see omega here. Okay, there's an alternative description. Well, okay, so first, actually, I wanted to say Kirwan has several different theorems. She has one theorem that lets you think about this generators and relations description. That's Kirwan's surjectivity theorem. Kirwan also has a theorem that says that the equivariant cohomology of M is a subring of the equivariant cohomology of the fixed point sets. And that lets you view equivariant cohomology as a subring of a direct sum of polynomial rings. And so this alternative description, so here on the left, we have a generators and relations. And then a number of mathematicians, starting with Francis Kirwan, then Sue Tolman and Jonathan Weitzman, also and in a different context, Goreski, Kotwitz, and McPherson find a description of equivariant cohomology as a subring. And I am not going to go into too many details, but I just want to sort of highlight that these two different descriptions might allow you to approach problems in different ways. What I will say is that generators and relations, these presentations are quite amenable to some kinds of computation, amenable to experimentation in Macaulay 2, for example. And there is a tremendous amount of work that has been done on that. Amenable to experiments, or maybe that's not the right word. Investigation via so for example, the subring description, I'll just say that it's harder to program, at least using with my limited programming skills. This is less amenable to that kind of calculation. But it has other uses, of course. Okay, so I'll leave it at that. The sort of the punchline that I've already let out of the bag is that we can hopefully make similar calculations in the complexity 1 case. So when a half-dimensional torus is acting on a symplectic manifold, this is the toric case, which has been well investigated. The next case is called complexity 1. So if we have dimension 1 less than half the dimension of the manifold, this is called a complexity 1 action. And so, for example, we're looking at a no action on a surface. We're looking at a circle action on a 4-manifold, a 2 torus action on a 6-manifold, and so forth. Okay, so that's what we're looking at. These as symplectic manifolds, we know about the classification of surfaces what these are. We know they have to be, to be symplectic, you must be orientable, and so these are classified by the classification of orientable surfaces. And then the next case of interest is what are these? And these, of course, as I alluded to, Hamiltonian circle actions, I alluded to the fact that these are always Kähler. These are classified by Carchon in the, oh goodness. The advantage of sitting in front of your books while you're giving a talk is that you can pull the book down that has the theorem. And the book was published in maybe 1999. Okay, so these were published in these were classified in the 90s. These I didn't say this here, but these are always Kähler. And the moment map, well, a moment map that goes to R, I mean, the image of the moment map can only be an interval. So somehow you need to pull out more combinatorial information. But these are classified by what are called decorated graphs. And so these decorated graphs have, they have fat vertices, so-called, which correspond to fixed surfaces. So the fixed points of a circle action on a 4-manifold can either be 0-dimensional or 2-dimensional submanifolds because they must be symplectic submanifolds. And then we also have isolated vertices, which correspond to isolated fixed points. And we have some edges and integer labels on the edges. Actually, no, those are in the natural numbers, they're positive. And the surface, the fixed surfaces, we have to label with their genus, their symplectic area, and their moment map value. These are also, the isolated are also labeled with moment map values. But from this, you can reconstruct the original manifold. And another point of Yael's work is, of Carchon's work, shows that there are minimal models, and then from the minimal models, you can construct all others by symplectic blowups. Okay. Similarly, Carchon and Tolman have classified complexity 1 symplectic manifolds. So the general case of a D-1 torus acting on a 2D dimensional manifold, and these are classified by the moment image plus some additional structure called a painting, which consists of combinatorial data as well as homotopy type data. So this is a bit more, this is quite a bit more complicated than the toric case, but the point is that they are classified and with data that we can write down. And so then natural questions are, well, can you compute topological invariance from this data?
Tara?
Yeah, Anton.
Yes, sorry, just could you remind us, you say they're classified up to equivariant symplectomorphism?
Yeah.
Okay, so
and there are multiple papers. I am always confused, and but there is a tall case and there is a non-tall case, and I don't want to get too too much into the details of which papers are out yet versus which are still in process.
Mm-hmm.
But yes, that is correct. Up to symplectic morphism. Okay, Tull case. Okay.
So in particular here, we do know about the symplectic structure. So this.
Yes. So here,
the decorations, images and decorations, they tell you everything about symplectic structure.
exactly. Yes. So symplectic structure is included in this data.
Okay, thanks.
Okay, so what can you compute from equivariant cohomology? So again, I'm going to have two sides. I'm going to have a subring. Well, there's a subring question and there's a generators and relations question. The subring version, actually some old work I did with Rebecca Golden in the case. So for both of these cases, the fixed sets are collections of isolated fixed points and fixed subsurfaces. And some old work I did with Rebecca Golden computes the subring version in the case when you have isolated fixed points. And then the first paper that I referred to in the on the very first slide, and I'll have the archive link again at the end, Liat and I were able to extend this to the case where you have fixed subsurfaces. So we have a subring description, and this subring version. So I said in the title of the talk, I talked about four manifolds, but this subring version works for general TD -1 acting on M2D. So this is in the general case. And I'm not going to give the details, I don't think, but I'll suffice it to say that this is the subring side. And the proof of this is soft. The proof uses the moment map, basically. And okay, so here's the picture. So I have this painting. I have this moment image with some additional data. So I know about the images of all the fixed points. I have to be careful in the case where I have fixed surfaces. The equivariant cohomology of a fixed surface has not just a polynomial ring attached to it, but the tensor product of that with the cohomology of the surface. And so the description is a little messier, but it is still a subring of something that I can have a handle on. And then what we do, so then what Liat and I do is in some ideal world, we'd like to have a generators and relations version for any, so over here again, we're still working on the general complexity one case. We can only find a generators and relation version for circle actions on four manifolds. The paper is surprisingly long. I'm not going to talk about the proof, but it is very hands-on. It relies heavily on this. It uses the subring version to verify that the generators and relations give you the ring that you are expecting. So it is not in some way. So the way that you can prove the Danilov-Yurkovich theorem is by way of Kerwin surjectivity. I do not know how to do that here because we don't have a construction of all of these manifolds by way of Kerwin surjectivity, by way of symplectic reduction. Okay, so this is a long paper, and what we actually prove is that for a complexity one space, we have something we take. So instead of Yael's decorated graphs, we define something called the dull graphs, where we throw away a little bit of information. And we prove that the following things are equivalent. So if we have two of these actions, then the dull graphs are isomorphic as labeled graphs, if and only if the equivariant cohomology rings. So here I'm looking at the even part being isomorphic, and then the odd dimensional ranks being the same. So the odd dimensional part doesn't play an essential role. And then this is also equivalent to a weak isomorphism. So it turns out that we classify precisely what you can, what isomorphisms are allowed of the cohomology ring that will not disturb the graph, or that will not be detected by this dull graph. And what I want to give you is an example where if in both of these examples, I am thinking about the circle action that corresponds to the moment map for the vertical axis. So here I have a moment map, here I have a moment map. These are both toric varieties, but if I want to think about just the second coordinate circle, they are complexity 1 spaces. And those two manifolds, it turns out for those two circle actions, they have exactly the same dull graph, but they, as a consequence of this theorem, they have weakly isomorphic equivariant cohomology modules. So these are two different manifolds. They I can see from the picture, so they are they have different symplectic volumes, so we can just say off the top that they cannot be symplectomorphic, but equivariant cohomology cannot distinguish them, or at least kind of because they have the same dull graph. And so one might ask, I mean, one can ask, I guess, for toric surfaces, these are both blow-ups. I've sort of drawn in the lattice points of a right triangle. These are both blow-ups of CP2, and you can write down the blow-up vectors. The blow-up vectors are different because they are different symplectic manifolds that we already see. We already see that from the symplectic volume calculation. But as complex manifolds, they are the same manifold. They are both blow-ups. Oh my goodness. 1, 2, 3, 4.
Tara?
5, 6, 7. Yes, they're both 7-fold blowups of CP2. Anton.
Yeah, apologies. You said it, but I probably missed it. Weakly isomorphic. What does it mean?
Sorry. Weakly isomorphic means isomorphic, but I can. So everything is as a module over HS1 of a point. This is just a. This is a polynomial ring in one variable. I'm allowed to change the. I'm allowed to change t and minus t. So I'm up to isomorphisms of z of t of polynomial of HS1.
Okay, but they
I didn't say that.
But they are you're saying they are isomorphic as modules, but not as rings?
Correct.
Oh, okay.
That's all that's all.
So you're having doubts? Or?
Yes, I'm trying to think of whether I'm saying something false. I don't think. Okay.
So
no, I mean as modules. And I don't think I want to dive into. I don't know what I can say about the ring structure. I'm going to say something false if I say 2. If I. I don't want to. Yeah. Okay. But I mean as modules.
Okay. Okay. Thanks.
The second part of this in the second part of this paper, we and the thing that we use to sort of identify the isomorphisms as a module, we give this generators and relations. So this is the generators and relations, and I sort of have written it down in a way that is suggestive of the Danilov-Yurkovich theorem. So I have generators. These generators are all degree 2. And again, I have multiplicative relations and linear relations. Yeah, so that's what the description looks like. And what did, right. So I wanted to tell you some of the consequences. Do I have time? I'm running out of time. And actually, I'm not sure if I'm supposed to stop at 10 of, or which would be over now, or am I allowed to talk until?
No, but I mean, like, it's a little bit negotiable, but I think since you started a bit later, I think you safely have 5-10 minutes, that's for sure.
Okay, good. Well, I have 5 minutes, so that's what I need. Okay, so some of the consequences, one of the things that we can directly prove, so when you're looking at a four-manifold, there are, and I'm not going to go into details here, but it was known that there are sort of finitely many inequivalent Hamiltonian circle or two torus actions, but the proof was by way of holomorphic tools, and we are able to deduce in a just using this description, which only comes from soft tools. So the point of this result is that this hard result is actually a soft result. Okay, so I'm not going to go into too many details about this, but this does let us bound this lets us deduce that we only have finitely many inequivalent actions on any particular manifold. And the other consequence, which is the joint work with Sue Tolman, is that there's a fourth equivalent statement in this first list. So we already saw by the example that I put up that the two examples we had were not symplectomorphic because they had different symplectic volumes. So that was a very cheap way to prove that. But it turns out that they are actually equivariantly diffeomorphic. So the symplectic structure doesn't come along, but the diffeomorphism type and the action come along from this generators and relations description. So right, and what I'm not going to right, the clock is ticking, so I can't prove the theorem for you. But what I will say is that there is a very explicit diffeomorphism that completely destroys the complex structure. But in the forthcoming paper with Sue and Liat, we very hands-only construct a diffeomorphism from one to the other. And precisely the issue in this example, I mean, and the point is with these four manifolds that everything is locally toric, and so you have very explicit local normal forms and local descriptions, and you can piece together, you can find very explicit diffeomorphisms sort of in the neighborhood of of something that needs to be flipped around. So those are the two words about what we do. Oh, right, and that was all I had. Oh, good, that's the end. So great, I'm under the bell. I didn't need a full 5 minutes.
Well, thanks a lot. Are there some questions or comments? So you can either raise your electronic hand or unmute yourself and just ask directly. I already had some questions, but maybe like I have at least one more somewhat technical question. I got a little bit confused, right? You briefly showed us those generators and relations, right? And then you said that all generators are of degree 2.
Mm-hmm.
So, but then from time to time you mention the odd cohomology groups.
Yes.
Like how do those things go together?
Yeah. So how the odd cohomology fits in. So first of all, one thing that is true is that part of the data that you need in this theorem is the ranks. Why won't this work? Whoops. What you need are the ranks of the odd cohomology groups. What's the explanation? I think it's just that everything is too small dimensional. So when you have a Hamiltonian circle action on a four-manifold, the odd cohomology is coming because the worst case scenario is that you have fixed surfaces and you can have at most two of them, one at the top and the bottom of the moment map, and they have to be the same genus, and the odd cohomology is just coming from that. And it has to play in a very rigid way with the module, the HS1 module structure. So somehow that's the explanation of the odd part. It's not really playing a role other than bringing along this surface.
That I missed. So they're basically only interested in the structure of the even.
Yes. So here, this is, sorry, I should have.
No, but now I see this 2 star.
Yeah.
Right. So we're only interested in but then
in the even part,
for the odd part, you have a much simpler, whatever, there is some statement about the odd part, which is
exactly. We compute it, it's then, but even the modular structure is there's not any freedom. So
I have perhaps, like, I don't know whether my next question makes much sense, but there is all this story of semi-toric, right there. You would be asking how, like, suppose you have another Hamiltonian which commutes with your S1 action, and then there is a huge classification and so on of how it all works. But then how do the two things fit together, right? Because we can say, suppose there is a semi-toric structure, then they have a classification, and then in particular, this would probably mean that their examples, they should fit into your classification in whatever, right? What would be, is there a link, or how does
that is a good question, and that tells me that I should go read some of those semi-toric papers much more carefully before maybe you've just delayed us putting our paper on the archive. I don't know the answer off the top of my head, but yes, I'm aware, and I can't tell you that quickly off the top of my head.
Maybe like what is a bit not confusing, but like they have some rather complicated system of invariants. 5 of them, if I remember, whatever, some kind of and then this would probably mean that all those things, they should give rise to whatever, like you should be able to say maybe what are your things.
That's right, and I haven't done that. I suspect that our situation is a very special piece of no. I suspect
your story is more general, right?
Everything is right. Our story is more general, that's right. So I have to look more carefully at that to say anything intelligent.
Okay, thanks a lot. Other questions or comments?
I have a question. What information do you remove from the dual graphs, like the values of the vertices? Anything else?
So
yes. You have like a picture, but I didn't manage to read it.
Right. No, I didn't actually say it either. Let me find the dual graph, or the decorated graph. So sorry. So what we get rid of for the dual graph we have to keep the genus. We remove the moment map labels and the area labels. And we add back in, so the moment, the area labels, okay, so I'm sort of explaining some of what's equivalent to what. There are some formulas from all of the data on this decorated graph. You can calculate the Euler class of the top surface or the bottom surface. And so we don't need all of the, that gives you, that's sort of a subset of this information. And so we add back in those Euler classes. Add back in a label that corresponds to the Euler class.
Okay, I think I understood. So you're saying like you can generate this, you can calculate this Euler class using the Distelman-Ekman formula from these
exactly,
and then you just remove it. Okay, thank you.
Okay, thank you. More questions or comments? If not, Tara, thanks again for a wonderful talk.
Thanks.
Yeah, it was nice to see you.
Yeah, it's nice to see everyone too. I wish we could go have lunch now.
Yeah, hopefully physical presence would come soon.
Yeah.
Right, so there will be the next Global Poisson in 2 weeks from now. Thanks everybody for attending, and see you in 2 weeks. Bye bye.